All right, so in the last few lectures, we found that there are two characteristics for a function to be differentiable. The first one is that there is a linear map, existence of a linear map rather. Existence of a linear map. So, if you have a function, if it is differentiable, there will always be a linear map which will approximate the given function. And the second part of the characterization is that the difference between linear change and nonlinear change is small compared to the independent variable h. We were calling it h, so h. So, these were the two characteristic features of a differentiable map. If a function is differentiable, there will always be a linear map, and this linear map will give rise to a linear change in the function. So, the second characteristic is that the difference between the two will always be small compared to h. What actually it means, I have already explained to you. Now, these two characteristics helps us to define a differentiable functions from Rn to Rm. So, now this leads to the following definition. This leads to the following definition for the most general case. Try to understand the point. In the beginning, we had observed certain difficulties in defining the idea of derivative for functions from Rn to Rm. The definition of derivative cannot be extended as such. So, what we did, we tried to look at the characteristics of the differentiable functions. So, we found some necessary and sufficient condition under which the given function is differentiable. The two conditions that emerged are these two. I have elaborated these two conditions earlier. Now, this gives rise to the definition of a differentiable function. So, I am writing down the formal definition by picking up these two properties. So, consider a function f from an open subset of Rn into Rm. I have explained to you the geometric interpretation of these two conditions as well in my last lecture. So, f is differentiable, pick a point P over here. So, f is differentiable, f is said to be differentiable at P if there exists a linear map we call it DFP, and this is from Rn to Rm. And a continuous function eta p such that the defining condition now I am writing on the top such that f of p plus h is equal to f of p plus dfph plus eta p h into modulus of h. So, if there exists a linear map dfp and there exists a continuous function eta p such that this equality holds, then the function f will be differentiable at the point p. Now, since dfp is linear, it will always be given by this dfp will be at h dfp h. Okay, let me write down. It will be f dash p into h. Now, this is a linear map from Rn to Rm. So, this f dash p must be an m by n matrix. Every linear map is written like this, a matrix multiplied by a vector. So, this is the vector h, it belongs to Rn. Okay, so, this is in fact you can say it is a n by 1 matrix. Okay. And this dot is in fact the matrix product. So, this is an m by n matrix, this is an n by 1 matrix, and the product of the two will be a m by 1 matrix, means the element of Rm. Okay. Now, we will work out what are the entries of this matrix. This matrix f dash p will be called a derivative of f at the point p. So, f dash p is called the derivative of f at p. So, the derivative of a function from Rn to Rm is a m by n matrix, and this dfp in this case, the linear map, is called the differential of f at p. Differential of f at p. Okay. So, this is the definition of the derivative. We have picked up the characteristic properties of the derivative and defined it is the most general case. Here everything is meaningful. Over there are certain things. In the first case, there were certain things which were not meaningful, and that is why we had to take help of some characteristic properties. Now, there are certain properties which we know that a derivative always has. An important property that all of us know, that if a function is differentiable at a point p, it will always be continuous. So, now we will check this property from this condition. So, this is an important property which I can write down as a lemma. It says that if f is differentiable, if f is differentiable at p, then f is continuous at t. Okay. Directional derivative does not have this property. Okay. There are other derivatives which do not possess this property. This is an important property. So, we will check it out from here. So, checking is easy. What you do, if it is continuous, then limit of f of p plus h must be equal to f of p. Yes. Is it right? So, I will consider this limit. So, by this defining equation, it will be limit of fp plus limit of f dfp. I have already shown you, it is f dash p into h and plus limit eta p h into modulus of h. H is tending towards 0. You can see that all these terms will become 0 in the limiting case. What will remain is this, and this is independent of h. So, you notice that limit of fp plus h is same as f of p when h goes towards 0. So, directly you show that every differentiable function at p is always continuous.
Limit f of p is free from h.
Yes, that's on the right hand side.
Right hand side.
Yes.
Limit h tends to 0.
Yeah.
F of p is free from h.
P dot, this one.
No.
So first term is
First term.
First term reaches.
I am saying for the first term.
So that side is not 0, sir.
Yes, yes, it is not 0, yes.
One is free from h, that side is not.
Their side, it is not 0. It is independent of h, you are right. All right, now see if there are other properties also. Now I will consider some example first. Now every time we will be using this definition for the differentiability of a function. There are some trivial cases, for example a constant function. Derivative we expect it to be 0. Okay, so we will see this holds or not for this definition. So let me consider a function f from Rn to Rm such that f of p for any p is equal to a fixed vector b in Rn, where b is a fixed vector of Rm. B is a fixed vector in Rm. So, since fp equal to b for all p, so f of p plus h is also b. So, let us see f of p plus h is equal to f of p, both of them are b. So, if there are any other term, they will be 0, because this is b, so everything else if I write down must be 0, is it right? So, what is that? This is in fact dfp. So, dfp h 0 means f dash p into h is 0, and this happens for every point, and therefore f dash p is 0, and similarly continuous function is 0. So, the derivative over here, that is f dash p, this implies f dash p is 0, is it right? Whatever h you choose, dfph is 0 means f dash p has to be 0. So, the derivative of a constant function is 0. Whatever point you choose, it is 0. So, that proves the fact that derivative of a constant function is 0. The next example, the trivial one, is that of linear map. If f is linear, if f from Rn to Rm is linear, then what will happen? Then f of p plus h, because of linearity, will be equal to f of p plus f of h. Okay? So, this I can write down as f of p, and this fellow will be dfph. Am I right? And plus nothing is there, so this 0. So, that means the difference between nonlinear and the linear change is 0. So, this fellow is eta p. So, eta p is 0. And what happens is that the differential of f dfph is what? It is in fact this FPH is this. So this is this shows what? This shows that DFP is same as F of P. Am I right? F of P plus H. Plus DFP H. Is it right? So what does it show? The derivative, this implies what? This implies DFP is same as F for every point, for all P. Okay, what is the argument? This is F of H. F of H. So, yes, this is equal to DFPH equal to F of H. DFPH is equal to, this is F of H. So, these two are equal, I am sorry.
So, here we have compared this to that formula?
Yes, I assume that this is differentiable. If it is differentiable, then this equality will hold.
Actually, sir, first you are writing the linear property, and second line you are writing from the definition.
Yes, from the definitions.
So, second line, sir, you should write by the definition.
Yes, this is by definition.
Sir, so this coming line side is coming from first step.
No, you see, the point is that if a function is differentiable, that this equality must hold. So what I will do, I will search out a continuous function, I will search out a linear map. If they satisfy this, the function will be differentiable. So what happens is, for this, I search out a linear map. A linear map over here, DFP I will search out, and I will search out a constant function, sorry, a continuous function, and plus FP is already there. Now, if I choose this function to be FH, okay, and if I choose this function to be a zero function, that this equality holds. Is it right? So, I have found a linear map, I have found a continuous map to satisfy this equality, and therefore I will say that yes, it is differentiable, and then the differential of f is same as f. So, this proves that DFP is same as f. So, differential of a linear map is same as the function f itself. Okay, so this was the example of some trivially differentiable functions. Okay. Now come to some other important properties of the differential of f and the derivative of f. The first lemma that I have is, let me see.
So is a differential function and linear?
If a function is linear, it will always be differentiable,
Yes.
and its differential will be same as the function. This is what we concluded. All right. Now the next thing is a lemma. This is lemma number 2. This says, if f is differentiable, if f from Rn to Rm is differentiable, then all directional derivative exist. Then all directional derivative exist. That is, directional derivative in all direction exist, and you can take it at a point differentiable at p. At p, then all directional derivative at p exist. And the relationship is that differential of f will be same as dv, इसको v कर लीजिए because you are taking a directional derivative, df. Okay, because the points in Rn are vectors, so instead of choosing p, you better choose v. Elements of Rn are vectors. Okay, no, vector is the direction, so trace. They are vector whether I write p or v, doesn't matter. Okay, all right. Now, so I have to show that all directional derivative exists. So the proof is easy. So we are assuming f is differentiable. So as f is differentiable, at p, then by definition there are many versions of the definition. I will choose this version. Limit f of p plus h minus f of p minus dfp h upon modulus of h equal to 0 when h tends to 0. If f is differentiable, then this condition will hold by definition. Okay. Okay, now what I will do in the next step, I will put h is a vector in Rn. So I will put h equal to some t times v, where t is a scalar. Okay, so if I put h equal to tv in here, this expression will become f of p plus t times v minus f of p minus dfp tv upon modulus of tv equal to 0. Okay. Now I can rewrite it as limit. Now since h tends to 0, so tv will tends to 0, tv will tends to 0 when t tends to 0. So v is fixed, t is varying, so you can change. So limit, I can replace it by, and I can bring this modulus of v out. So this becomes f of, I can put a bracket here, f of p plus tv minus f of p, and minus, since dfp is linear, t will come out, it will be dfpv divided by t, and this is 0. Okay, so it becomes limit t tends to 0, 1 upon modulus of v, I can write down here, and here this term in the limiting case will be directional derivative of f at p minus, in the second term t will cancel t and it will be simply dfp v equal to 0. Now look at this. This thing equal to 0 and this is non-zero, so it gives me dvfp is equal to dfp, and this is what you wanted to prove. So the thing is, whenever a function is differentiable, if you want to compute its differential at a point v, that will be nothing but the directional derivative along v. Okay, so this is how sometimes differential of f is computed in terms of directional derivative. All right. Now there are some consequences of this property. So let me write down this relationship. Lemma 2 says that the directional derivative of f, if f is differentiable, so first I write down dfpv is in fact dv fp. Okay. Now the third lemma says the following: if f is differentiable, if f is differentiable at p, then dv fp will be equal to some vi in terms of directional derivative del f upon del xi. I is running from 1 to n, and this dvfp is dfpv also. The first equality I have already proved, okay? Only I have to look at the second equality. Here V is a vector in Rn, okay? So V will be equal to some component, let us say V1, V2, V3, Vn. So these are the components of the vector which I am denoting by Vi. I can also rewrite it as, instead of this I can also write it down V1 E1 plus V2 E2 plus Vn En, where E1, E2, E3, En, they are the basic vectors of Rn. Alright, so with this understanding I have to work out this formula. So proof. So I have function from Rn to Rm, and if I pick a point over here, Fp will be a vector in Rm. Being a vector of Rm, it must be written as some F1p, F2p, and so on, Fmp. This is the image of P under F. These F1, F2, Fm, they are the components of F. Okay, and how do you obtain them? Fi will be equal to Yi composition F. Is it right? What are Yi's? Yi's are coordinate functions on Rm. These are coordinate functions. I have already told you what coordinate functions are. So this is how Fi are defined. So you can see you have a function from Rn to Rm. This is F, and then you have Yi's, coordinates of Rm, and they will land you into R. So these are composite function, and they are Yi composition F, and you are calling it Fi. So each Fi is a map from Rn to R. Okay. All right. So I have to show, so let me start computing dv fp. This I have shown in the earlier lemma, it is dfp of v, is it right? And now I can rewrite it as dfp, v I have rewritten as v1 into e1 plus v2 into e2 plus so on Vn into En. Now use the linearity of dfp, it will be written as Vi dfp Ei. Am I right? Summation I runs from 1 to n, there are n components. And this dFPEI, again by the last lemma, it will be I equal to 1 to n Vi, they are DEIFP. And this DEI means partial derivatives of f. Okay, you remember? Directional derivative along the basic vectors are nothing but the partial derivative. So, I get I equal to 1 to n Vi into del f upon del xi, and every time it is being calculated at the point P. So, this is exactly what we were to do. Is it right? So, you have got another equality. This is summation I 1 to n Vi del f upon del xi at the point P. All right, with the understanding that Vi's are the components of V. Now, if you, in particular, as a corollary, before writing down the statement of the corollary, let me tell you that if f is a function, from Rn to R, then you know there is a vector called gradient of f. We also call such function as scalar fields. So, gradient of f, then gradient of f, or we also say like this, del f. This is a vector of Rn, and this vector is given by del f upon del x1, del f upon del x2, del f upon del xn. Whatever point you are choosing, these are the derivatives over there, partial derivatives. It is called gradient of f. Now, if f is a function from Rn to R, look at this relation, last relation. Okay. In this case, in which case, when the function is from Rn to R, dVFP as well as dFPV is dVFP, which is equal to this much, and this much I can write down as the inner product of delta F at P into vector V. Look at this inner product will be nothing but this quantity. Is it right?
Yes, sir.
So, this is another way of computing the derivative of a function. So, the derivative of a function at V will be nothing but the inner product of gradient of f and inner product of and V. So, this is also an important relationship.
The gradient of f is the derivative of, is the generalization of derivative in multiple directions.
Yes, that is also defined, but now I am taking it a real valued function. But if you have function from Rn to Rm, then you have multiple directions.
What is the difference between gradient of f and the Jacobian?
I am coming to the Jacobian. You will see the relationship. Okay. So, now we are in a position to discuss the Jacobian at this point. Yes, we can do that. So, let me write down the relations that we have in hand. The first relation in terms of the differential of f is, this is f dash p into V. Okay. F dash p is a vector, sorry, matrix, and V is a vector, and this product is the matrix products. Okay, I am putting a dot, but this means a matrix product. Okay. Another relationship, this is number 1. And relation number 2 is dfpv is also equal to dvfp. Okay, and this is also equal to summation vi, and for real valued function this is true, but for in general it is not. Okay, all right. Now, so this matrix I want to know in terms of the partial derivative, because here the relation was in terms of the partial relationship. So now come to the idea of Jacobian matrix. We also call this matrix as the Jacobian matrix. What we want to do now is to look at the entries of the Jacobian matrix. We will come to know that these entries are nothing but the partial derivatives. So, Jacobian matrix. Okay. So, okay. So, I should start from here. So, let me consider a function which is differentiable. Point I am not mentioning, it is differentiable somewhere at a point P. So, point will always be understood. So, dvfp is, so first of all let me write down fp. So, fp as I told you is f1p, f2p and fmp. In short, we also write it down. In short, we also write it as f equal to f1, f2, fm. There are m components of f. Okay. Now, what we can easily check by ourselves, that directional derivative of f at any point p wherever it is differentiable, it will be same as the directional derivative of f1 at p, comma, directional derivative of f2 at p, and so on, directional derivative of fm. Okay, so this relationship one can easily check, this holds. Okay, now I am going to make use of this relationship. Now, since each fi, f1, f2, f3, fm, they are real valued functions on Rn. So, each fi here you can see is a function from Rn to R. So, whenever you have a real valued function which is differentiable at a point P, I can make use of the second relation. What was the second relation? So, this implies that dvfp is equal to, if f1, f2, fm all of them are real valued, so I can make use of that last relation which says it is equal to summation vi into del f upon del xi f1. You remember? Yes. Similarly, in the second place, I is running every time from 1 to n. Vi del f2 upon del xi, and last one is the same, Vi del fm upon del xi. Okay? Yes. Now, these relations I can rewrite as, look at them closely. Okay. So, what do you notice? Now, this I can write down in the form of a matrix. what I will do, I will write down delta F1 upon del x1, del F1 upon del x2, and last entry of the row is del F1 upon del xn. This is the first row of the matrix. I will multiply first row with first column. You see, when you multiply this row with this column, you will be getting this. Is it right? And the second entry, in the second row, sorry, I will be writing del F2 upon del x1, del F2 upon del x2, del F2 upon del xn. Same thing here. When you will multiply the second row with this column, you will be getting this, and so on. So, and this vector right side, in fact, if you see, you can write down as a column vector as well.
Yes.
Okay, you can write down this as summation vi del f1 upon del xi, and so on. Last one will be summation vi del fm upon, you can see. Okay. Now I will recall, last row will be del fm upon del x1, del fm upon del x2, del fm upon del xn. So the product of this row with this column vector will be this fellow. Huh? Okay. So now I am going to finish this. If you remember, it will be dvfa is also equal to, sorry, f dash a, dfa, dfp of v is also equal to f dash p into v. The left extreme side is also equal to dfp v. So if you write it down as f dash p into v, sorry, f dash p into v, matrix multiplication here, then you can see that this matrix is actually equal to f dash p. So the Jacobian matrix of the derivative is actually this matrix of partial derivatives. So f dash p is the matrix of partial derivatives. And this is known as Jacobian matrix. Okay. All right. So I stop at this point. There are some other properties of the derivative which we already know for the case of function from R to R. For example, it satisfies the chain rule whenever you have a composite function. The same thing you can see over here also. Chain rule is satisfied by functions from Rn to Rm as well. And the last thing that I will be talking about is the inverse mapping theorem. This is one of the fundamental theorem, inverse mapping theorem, and consequently the implicit function theorem. Okay, I stop at this point. Okay.